Good afternoon, and welcome again to this lecture of electronics, in which we were studying communication, right? So we have completed almost all sorts of communication except phase modulation. So we'll be continuing that in the next, next lecture, coming lectures. So phase modulation is there, and I need to show you animation of that also. But today we are going to continue with this, the same, which we call it as, yeah. So the amplitude modulation, I guess my screen is visible to you. Is it visible? Yeah. So we need to just brush it up what we have studied in the amplitude modulation and what is actually the equation of that amplitude modulation, right? So just I need to tell you that. So let me introduce myself. Myself, Dr. N.D. Meshram, Head and Associate Professor, Department of Electronics, SHRI MATHURADAS, MOHOTA College of Science, Nagpur. And today we are going to continue with this amplitude modulation. So we need to learn some equation portion of this. So yeah, the definition was the amplitude modulation is a technique of modulation in which the instantaneous amplitude of the carrier wave, remember this, the word, in which the instantaneous amplitude of carrier wave, carrier signal varies in accordance with the amplitude of modulating signal, right? While frequency and phase of the carrier remains constant. Nature of amplitude modulated waveform are shown below. So we will be showing you that. So this is the basic definition we have studied, and we need to keep this frequency and phase as constant, right, of the carrier wave. Okay, so this was the equation. This was actually the waveforms that we have shown you in the animation. So this is supposed to be the low frequency modulating signal, which is having very low frequency, and then we are using this carrier signal to carry this low frequency to a distance plate, right? So this was the high frequency signal, which we are calling it as a carrier wave. And when we modulate this, we'll be having this type of waveform, which we call it as the amplitude modulated wave. Yes, I guess I have already shown you that. So this is the envelope which is over there. And depending on this amplitude of this modulating signal, the envelope is going to vary, right, as shown in this. So the signal, the modulating signal is trapped between this envelope of say the amplitude, right? So higher amplitude Vmax and Vmin. In between that, we are having our original signal which we need to transfer. Okay. So hello, am I audible? Hello. Hello, am I audible?
Yes, sir.
Thank you. I guess my voice is not coming over there. That's why I'm asking you. Okay. So this is the modulating index that we are basically concerned with. Modulation index means how much modulation we are going to do. So in AM, the modulation index M is defined as the ratio of amplitudes of modulating signal to the carrier signal. Now this is the basic definition of the modulation index. The amplitude of this carrier is this modulating signal, as well as the amplitude of this modulated signal, right? So this is the equation of that. This is the formula for that. The modulating signal amplitude with respect to divided by the carrier signal amplitude. Okay, and that is equal to EM by EC. They are being represented by that. And if modulation is expressed in percentage, it is called percentage modulation. Now this is very, very important, because we need to know how the waveform which we are expecting to get out of the modulated circuit, that how it appears, right? So that is in percentage can be written as EM by EC into 100, and referring to the figure 2.6, the modulation index will be Vmax minus Vmin divided by Vmax plus Vmin. So we are going to calculate the average, and here this is how we are going to calculate the modulation index. We will not go in depth of all the equations. Now, what would be the effect? That is what I need to show you. So what is the basic effect of the modulation index on modulating signal? Now what happens? Just look at this. So if the modulation index is less than 1, remember this, if modulation index is less than 1, that is EM is less than EC, then what happens? We will be having under modulation, right? So the difference between this EC and EM will be very small, right? So that is nearly equal to the modulating signal. Say, so that is why we don't require this type of under modulation, right? And what happens when we have both, that is the modulation is in modulation index is equal to 1, then we'll be having EM by EC, that is modulation index is 100%. But here, this, if you are see, so with lower half, that is in the negative half, the output will be in the modulating signal will be like this, right? With the, whereas at upper half we will be having this high. So we call this as a fully modulated signal. And what happens if the modulation index is greater than 1, that is EM is greater than EC, then we'll be having a clipping distortion, that is there will be no signal at this, right? So we call it as the over modulation. So this is not acceptable, right? So this is the carrier wave, and so this is the carrier wave, and here EM will be equal to EC, and we call this as no modulation, where M is equal to modulation index is 0, then there will be no modulation, right? So this is the basic effect of modulation index on the modulated signal that we are expecting to appear across the output of a modulator. This is when M is less than 1, this is M is equal to 1, this is M is greater than 1, and this is M equal to 0. So if M equal to 0, which implies that there will be no modulation. Okay. So what happens if we use a triangular waveform as a modulating signal? If you put it to this circuit, and the input signal is now a triangular triangular wave. This is the input wave that we are supposed to say transfer. So this is a carrier wave. This will remain same, and when we put it modulated, the wave will look like this. So as you see, this is actually the amplitude of the carrier wave is going to change, right? So according to the amplitude of the modulating signal, this is what I need to show you all the diagrams over here. So yeah, so what happens to it if we apply a square wave as a modulating signal? So we'll be having these types of waveforms. So depending on the input signal or modulating signal, depending on the amplitude of the modulating signal, we'll be having these types of output waveforms, or we call it as amplitude modulated wave. So here, as you can see, in the negative half of the square wave, where it is 0, we consider it 0, then we'll be having a lower amplitude, whereas in the positive half we'll be having a higher amplitude. Now again, the carrier wave is trapped in between that, between the signal, and it is forming an envelope of it, right? So this is for the square wave, and these are some of the equations, examples, which will not talk here. So yeah, these are all equations. So this is all about, say, the amplitude modulation. I guess you have understood this, and what is a modulation index required for, say, the wave, carrier wave, to transfer the data, right? So this is the amplitude modulation. I will again repeat it for you. This is the definition. That is, the amplitude modulation is a technique of modulation in which the instantaneous amplitude of a carrier signal varies in accordance with the amplitude of the modulating signal, keeping phase and frequency as constant, right? Then this is the modulating waves, modulating signal. Then this is a carrier wave, and this is the amplitude modulated wave, right? Then yeah, this was the modulation index. Modulation index is defined as the ratio of amplitudes of the modulating signal to the carrier signal. So we'll be having the amplitudes of both, and they are being represented by EM and EC. EM is the amplitude of the modulating signal. EC is the amplitude of the carrier signal, right? So we'll be having the ratio of it. And if you need to calculate the percentage of the modulation, then just multiply this product, this term, by 100, then you'll be getting 100 say percentage of modulation. And depending on this percentage of modulation, yes, of course, we'll be having the modulation index, that EM can be calculated as Vmax by Vmin. Similarly, here we will be having again Vmax plus Vmin. So the modulation index it can be calculated in this fashion also. But what the role the modulation index plays is, because of that we come to know that how much modulation is being performed and how will be the output of that. So this is when the modulation index is less than 1, that is EM is less than EC. Since we are working on, say, the amplitude of that, therefore we are using this, and this is the envelope. So if it is M is less than 1, then we'll be having under modulation, which implies that both the amplitudes will be nearly equal during the negative half as well as during the positive. Okay, and when we are having M equal to 1, we call it as fully modulated. Here it is actually, here it should be a slight curve, right, which will show you some wave over here, right? It is not 0. Here it is showing you 0, but it is not exactly 0. Here it should be something on the above 0 level and below 0 level, right? So a small region will be there, but still, yeah, we can call it as say fully modulated signal, right? So this is the when we are having a modulation index equal to 1, and similarly when modulation index is greater than 1, then we call it as, that is EM is greater than EC, we call it as the clipping distortion. Yes, this is the over modulation. Here in this, I guess it is not proper. It should be a very small line, right? So something should appear on here, which we are going to call it as a fully modulated signal. Whereas here it is clipping distortion. Yes, exactly, it is a clipping distortion because we will be not having the negative half, which is to be modulated. And we call this as over modulation. The peak will be highest and here it will be 0. Okay. And if it is the modulation index is supposed to be 0, then the carrier will appear as it is. Okay, we call it as no modulation is done in that. So we'll be having a simple carrier wave frequency like this, what is whatever is shown on the screen over here, right? This is when we'll be having EM equal to 0 or EC. EC will be this. So EM equal to 0 implies that we'll be having modulation index as 0. Okay, so this was for the sine wave. And for triangular wave, if you apply triangular wave as a modulating signal, and if you need to modulate it and put it to the circuit, then I guess it will appear like this, right? So it is nothing but change in the amplitude, which is supposed to occur over here. So since it is an amplitude, since it is a triangular wave, therefore we are having a triangular waveform on this triangular envelope on this amplitude modulated wave, right? So depending on the amplitude of the modulating signal, we'll be having the modulated signal like this. So for this, this is for the triangular modulating signal. Similarly, for the square wave modulating signal, will be having 0 to plus 5 volt, and it will again return to 0 to minus 5 volt as say suppose. And during this positive region where it is say positive, will be having a higher side of the amplitude. Similarly, during the negative half, we'll be having a smaller amplitude comparatively with respect to the positive. Okay, so this will be the amplitude modulated wave for a square wave. So depending on the modulating signal, depending on the amplitude of the modulating signal, accordingly the envelope of the signal is being varied, right? Now these are some of the examples where we need to calculate. I guess we are having this AM waveform for the modulation index 0.75, M equal to 1 and M equal to 1.25. So we need to calculate in these three modulation index. So we are having this EM by EC equal to 0.75, EM by EC equal to 1 and EM by EC equal to 1 by 1.25. So we need to calculate less than 1, equal to 1 and say greater than 1. Okay, so this is the waveform which can be drawn for the modulation index, which is equal to 0.75. Then yes, so for 0 we might be having like this, or say for M equal to 1 we'll be having this, and for say 1.25 will be having this. So we'll call it as a clipping distortion, right? So here it is showing a little bit of that when the modulation index is equal to 1, which implies that we are having a fully modulated signal. So it will show like this. Okay. And here it will be having the clipping distortion. So this is some of the examples. And in the next class, we are going to study the frequency spectrum of amplitude modulated wave, which is nothing but how the frequencies are being, the bandwidth are being placed in amplitude modulation. So I guess we will stop over here. If you have any questions, you can ask me on this. So thank you very much for joining. I will be uploading more videos of electronics on my YouTube channel. Please go through my YouTube channel, watch, like, and share my videos. And say if you have some queries, just put some comments on my channel itself so that I can rectify those. Thank you very much. Stay home, stay safe, take care, and please be precautious. Good day. Bye. See you in the next class.